Hi everybody, in this next section we're going to continue our journey into the world of integrals, and we'll talk about another technique of solving particularly nasty integrals called inverse substitution. So this is going to be a problem-driven session where we'll talk about inverse substitution, what it is and when you can use it, so particular cases where it's useful. And then we'll also talk about a number of different substitutions that you can use for similar looking expressions involving higher order roots more than square root, or particular rational functions of sine and cosine. So let's start off by talking about inverse substitution. And you might wonder, well, I know about substitution, so what is inverse substitution? So for direct substitution, or just substitution, what you did is you replaced a variable in your integral by an expression, and that then let you simplify the integral. So you replace part of the integral with a new variable. That's what substitution did for us. And for instance, what we used to do is we, for instance, had integrals of the form sine 1 minus x dx, and then we would call 1 minus x equal to t, and therefore we could write this as sine t dt with a minus. So what is inverse substitution? The subject of today. Here you replace the variable of integration by a function of a new variable. So here, for direct substitution, it was part of the integral that we replaced, like 1 minus x. And for inverse substitution, we'll just replace the variable itself by a function of a new variable. So for example, how does this work, or what does this do? Let's take, for instance, the integral of square root of 1 minus x squared dx. By itself, we can't really make sense of this, but there's a particular trick that we can use here. We can put x equal to, for instance, sine of theta, and then dx becomes cosine theta d theta, and with these substitutions, the integral becomes square root of 1 minus sine squared theta, and dx is cosine theta d theta. So now you know 1 minus sine squared, that is cosine squared. We have cosine squared, the square root of that gives me cosine, so I'm left with the integral of cosine squared theta d theta. And now this is a slightly easier integral to solve. Actually, we encountered this integral in one of the previous classes, so we would then write this as 1 plus cosine 2 theta over 2 d theta. And this integrates to theta over 2 plus sine 2 theta over 4 plus a constant. And now we have an answer in theta, so we have to replace that by an expression in x. For that, we go back to our original expression. So if we substitute x equal to sine theta, we also know that theta is the inverse sine of x. And so now substituting that back in the expression, so we use that to get the results in the last step here, we get sine inverse x divided by 2 plus sine of 2 times sine inverse x divided by 4 plus c. And now there's one last simplification that we can make. We have that sine of 2 times sine inverse, so that we can simplify as well. So let's do that on the side. Sine 2 times theta equals sine sine 2 times sine inverse x. That's what we want to simplify. So we already know that sine theta is x. We know that sine 2 theta is 2 times sine theta cosine theta. So let's use that. 2 times sine theta cosine theta. Sine theta by itself, that's x. And then cosine theta, that becomes square root of 1 minus x squared, because cosine is square root of 1 minus sine squared. So all in all, what we have for sine to theta is that this becomes 2 times x square root of 1 minus x squared. And now, using that to finally simplify our integral, we get sine inverse of x divided by 2 plus x square root of 1 minus x squared, also divided by 2, plus a constant. And in particular here you see that for this integral to make sense, x should be between -1 and +1. Otherwise this factor becomes imaginary. And that is also implicit in the definition here. When we made our substitution, we said x is sine of some angle theta. That is only going to work if x is between -1 and +1. So that's a particular example, and again you see the salient feature. What we do is we don't rewrite the integral so much, we just substitute the x wholesale for a function of another variable theta, in this case sine theta. And now the question is, well, how do you remember what form to use or what to use when you're confronted with an integral like this? And the answer is that oftentimes it depends on the form of the integrand. So in particular, if you have something that's 1 minus x squared, substituting sine or cosine is going to be a very good idea. And to make that a bit more concrete, we have a couple of special. So for the first case, we'll look at the case where the integrand has a factor square root of a squared minus x squared with a positive. And here we'll use the substitution x equal to a sine theta, because then that square root becomes a squared minus x squared is a squared 1 minus sine squared is square root of a squared cosine squared theta, and that's a times cosine theta. So let's look at an example. Let's take the integral dx 5 minus x squared to the power 3 halves. So 3 halves, not just square root, but 3 halves. You can write that as a square root raised to the power 3, so it still fits within this general pattern. The substitution that we'll use here is x equal to square root of 5 sine theta. So that means that 5 minus x to the power 3 halves is 5, then 1 minus sine squared, that's cosine squared, raised to the power 3 halves. So that is 5 square root of 5 cosine to the power 3 of theta. And likewise, the differential dx becomes square root of 5 cosine theta d theta. So then our integral becomes square root of 5 cosine theta d theta, and then divided by 5 square root 5 cosine to the power 3 theta. And so that simplifies to 1 over 5 d theta divided by cosine squared theta, or 1 over 5 integral of secant squared theta d theta. And that then gives us the answer straight away. So the integral of secant squared is the tangent of theta plus a constant. And now we have to determine what tangent of theta is given sine of theta. So for that we have to sketch a triangle, right angle triangle. We put theta here, and from the fact that x divided by square root of 5 is sine theta, we can deduce that the sides in our triangle are the following. So the opposite side is x, the hypotenuse is square root of 5, and that gives us x over square root of 5 for the sine. And then Pythagoras' theorem tells us that the adjacent side is 5 minus x squared, the square root of that, and therefore tan theta is the opposite x divided by the adjacent 5 minus x squared. And now we can conclude our problem by substituting that into our expression. We have 1 over 5 x divided by square root of 5 minus x squared plus c. So now the next case is of course the one where it's not minus, it's plus. So here we have an integrand with a factor square root of a squared plus x squared. So that's the difference with the previous slide, and again we will assume that a is just positive. And more generally, this trick will also work for factors of the form 1 over a squared plus x squared, and even for a squared plus x squared to some power p over q, but not for all power. So for some power p over q. So I can't give you a recipe for where it will work and where it will give you an integral that is tricky. You just have to try and see if the substitution gives you something that you can work with. So in this case, what we will do is we'll use the following substitution. We'll put x equal to a times tan theta. And so from that, we have that the expression that we're interested in, a squared plus x squared, is a squared 1 plus tan squared theta, and that is equal to a squared divided by cosine squared theta, or a squared secant squared theta. So let's see an example. Let's look at the integral of dx, and now we'll combine both cases, square root of 1 plus 4x squared. So in and of itself, this isn't exactly the case that we started from, because we have 4x squared, we don't just have x squared, but we can sweep that up in one go. What we can do is we can substitute 2x equal to tan theta. And why 2x? Well, 4x squared, we can write that as 2x squared And either we do a substitution to get rid of the 2 and then an inverse substitution, or we do both in one go. And I'm doing the latter here. So 2x equal to tan theta. And then for the differential, we have 2 times dx is the derivative of tan theta, so it's cosine 1 over cosine squared theta d theta. And so dividing by 2, we have dx is d theta 2 times cosine squared theta. Okay, so what does that give us for our integral? So the dx becomes d theta 2 times cosine squared theta. And then what do I have in the denominator? Well, I have the square root of 1 plus tan squared theta. And 1 plus tan squared theta, I know that that's 1 over the cosine squared theta, so I can squeeze that in. This is 1 over the cosine squared theta, and therefore we can simplify our integral to 1/2 d theta cosine squared theta, and now I have the square root of 1 over cosine squared theta, so that gives me a 1 over cosine, so I get 1 over cosine theta, and of course the cosine square and the 1 over cosine simplify to give me d theta over cosine theta, or in other words the integral of secant theta d theta. And I'm writing it like this because, again, this is a trigonometric integral that we've already solved. And we know that this is equal to 1/2 the logarithm of the absolute value of secant theta plus tan theta plus a constant. So now, what do I know about the constituent parts? Well, secant theta is something that I will have to compute, and tan theta I already know from my substitution. This is x over 2. So let's compute what secant theta is, and again we have to take recourse to a triangle to find that out. So if I take my right angle triangle and I call one of these angles theta, then from my substitution I know, well, tan theta is 2 times x. So what I can do is I can put 2x for the opposite and 1 for the adjacent to get a tan of 2x. And then Pythagoras' theorem tells me that the hypotenuse is 1 plus 2x squared, so 1 plus 4x squared, and then the square root of that. And why do I want to know the hypotenuse? Well, the hypotenuse is important because now I can use that to compute the cosine. So I know cosine theta is the adjacent divided by the hypotenuse, 1 over square root 1 plus 4x squared. And it's not really the cosine that I'm interested in the secant. So the secant of theta is 1 over the cosine, and so that gives me square root of 1 plus 4x squared. And now I can finish my exercise. I know that secant is 1 plus 4x squared, and I can put everything together to get 1/2 logarithm of absolute value square root of 1 plus 4x squared plus x divided by 2 plus a constant. And I made a small mistake here. This should not be x over 2. This should be 2 times x, so 2 times x, and then here I also have a 2 times x. So just to make it clear, this is my final answer, modulo the small mistake that I made earlier. So that gives us the case where we have a squared plus x squared. So for the last case, we'll consider the case where the integrand has a factor of the form square root of x squared minus a squared, again with a positive. And here we will have to be a bit careful. So if you look at the square root, then you have that x squared has to be bigger than a squared for the square root to make sense. If it's less than a squared, then the x squared minus a squared is negative, and the square root of a negative number gives you something imaginary, which we don't want in the context of our integral. So we have to assume that x squared is bigger than a squared. And then this in turn leads to two separate cases. So either x is bigger than a, or x is bigger than or equal to, or x less than or equal to minus a. So here the substitution that we're going to make is the following. We'll put x equal to a times the secant of theta, and then square root of x squared minus a squared becomes square root of a squared secant squared minus 1, and that simplifies to a times square root of tan squared theta, and square root of square, that cancels, but you have to be a bit careful. The left hand side is a square root and therefore is positive, so we want the right hand side also to be positive. So here we need to take the absolute value of tan theta. And taking an integral of an absolute value is also a bit difficult, so that's where our case analysis is going to come into play. So let's look at an example, and let's try to compute the integral of dx x squared minus a squared square root of that. So then we know what the square root is in the denominator. We just need the expression for dx. So dx is then a times the derivative of the secant, so that's secant theta times tan theta d theta. So with that we can substitute in our integral, and we get a secant theta tan theta d theta, and then divided by a times absolute value of tan theta. And we can cancel the a, that's very easy to do since it's positive. And now what we want to do is we want to have a look here at this tan theta divided by absolute value of tan theta. So for that we're going to have to look at two cases separately. So case 3.1, here we assume that x is bigger than a, and so in particular x and a are both positive, so xa positive, and therefore from the rule that links them with theta, we have that secant theta is also positive or 0, and therefore tan theta is positive as well. And so if we call our integral I, then our integral becomes integral of secant theta tan theta d theta divided by, and now absolute value of tan theta. Tan theta is positive, so that becomes tan theta. That means that these two expressions cancel, and we're left with the integral of secant theta d theta. This is good because we know what the integral of the secant is. It's the logarithm, natural logarithm of the absolute value of secant theta plus tan theta, plus a constant, of course. And now we go back to where we started from, our expression. We know that x is a times secant theta. So secant theta by itself is x divided by a. And now we need to figure out what tan theta is. And for that, we're going to draw another triangle. And let me maybe do it down below here. Right angle triangle. And we have that x divided by a is secant. So a divided by x is the cosine of theta. And we can represent that graphically. If this angle is theta, then the adjacent side is a, the hypotenuse is x, and the other side, the opposite, is square root of x squared minus a squared. And then from this triangle we also get that tan theta is the opposite divided by the adjacent, so that's square root of x squared minus a squared divided by a. So now we can come back to our expression down below here, and we can write this as square root of x squared minus a squared divided by a. There's one last simplification that we can make with the integral. So let's write down what it is. Ln of x divided by a plus square root x squared minus a squared divided by a plus a constant. Now we have this common denominator a here, so we can write this as x plus square root x squared minus a squared divided by a plus c. And now logarithm of a fraction, that's logarithm of the numerator minus logarithm of the denominator. So ln x plus square root x squared minus a squared minus the logarithm of absolute value of a plus c. And now just an aesthetic simplification that you can do. So c is an arbitrary constant, and we add to that this constant ln of absolute value of a. So adding a fixed value to an arbitrary constant, that doesn't change the arbitrary constant, so we can call this a new constant c prime and absorb the ln of a. So our final answer is ln x plus x squared minus a squared plus that constant. C prime literally, but C prime or C, that's notational difference. And then that gives us case 3.1. So for case 3.2, you have to assume that you're in the opposite case where x is less than minus a. And so in particular, here we have that x is negative and a is positive. And from that, if you look back at the definitions, you can deduce that tan theta is also going to be negative. And then the integral becomes a times secant theta tan theta d theta divided by negative a times tan theta. You have cancellations, constant of course, the tan drops out, and you have minus secant theta d theta. And so now we can continue pretty much on the same trajectory as before. So the integral becomes minus the logarithm secant theta plus tan theta plus a constant. And now we have to rewrite things back in x. So let's go back at our triangle. And let's fill in what we already know. So this was theta. This was x squared minus a squared. We have a for the other side and x for the hypotenuse. And now you might be tempted to say, hey, I know that secant theta is x divided by a, so that's still correct. Tan theta is square root of x squared minus a squared divided by a, the formula from the previous slide. But that is not exactly true because we know tan theta is negative. We deduced that from our case analysis. And what we have here on the right-hand side, that is a positive expression, square root divided by a, which is positive. So we have to make that negative by putting a minus sign in front of this. This is again what you have also in trigonometry, where the triangle gives you the relation between the different quantities, but not always the right sign. So you always have to think carefully about what you have, whether it's positive or negative, and therefore if you have to adjust the signs. So with that, let's continue our integral. Get minus logarithm of absolute value x over a minus square root x squared minus a squared divided by a plus a constant. And now let's work on that a bit more. So with the same reasoning as before, we can write this as negative the logarithm of x minus square root x squared minus a squared plus a constant. So again, we took out that a and absorbed it in our arbitrary constant. And now let's do something about these signs. So what we're going to do is rewrite the interior as follows. And multiply by the conjugate plus a constant, and then the numerator becomes x squared minus x squared minus a squared divided by x plus x squared minus a squared. Okay, so now here the x squared and the x squared cancel, and we have minus the logarithm of a squared x plus square root x squared minus a squared plus c. So I'm no longer writing the absolute value signs because a squared is always positive, but you could write them if you wanted to. And now we have again logarithm of a fraction, so let's split it up into negative logarithm a squared, and then minus, so plus the logarithm of absolute value x plus square root of x squared minus a squared plus a constant. And now again, we take this thing, logarithm of a squared, which is a constant in its own right, and we have this arbitrary constant c, and we again absorb that and redefine our constant c. So in your integral expression, once again, if you peel off these constants, you can just lump them together with the arbitrary constant and just call all of that c. And that leaves us with logarithm of x plus square root plus a constant. And now if you see, the expression is exactly the same as the other case. So here we have the same expression as the other case. So lastly, we've seen these different cases and they have a particular expression. But you have to keep in mind that not every integral will be precisely of this form. In some cases, you have to do a little bit of work to reduce it to a particular form. And completing the square is again a very useful technique to do that. So let's say we have an integral with x squared plus 4x plus 5 in the denominator. Then what we can do is we recognize this x squared here. So we have an inkling that probably it's going to be one of our three cases that we've seen. We don't know which one. So let's try to write it as a real sum or difference of two things. So we can do, this is x squared plus 4x plus 4 plus 1. And then here we recognize that this is x plus 2 squared. So in order to do completing the square, what you basically end up doing is you look at x squared and 4x, and that tells you, well, if I have a square of this form, x plus a squared, then that's x squared plus 2ax plus a squared. So the first two terms here give you the first two terms in the square, and then you have to adjust a for what the coefficients are and what you have. So this is typically x squared plus 2ax, and in this case a is 2. So we know, okay, we need to add an a squared of 4. And then once you have that, you're in a good position to simplify the integral. So now we have x plus 2 squared plus 1. We do a substitution and call this t, and we have dt t squared plus 1. And now we know we're back in one of our generic cases that we talked about earlier, where we have t squared plus a squared. And so we can immediately write down the answer, which is inverse tangent of t plus a constant, and therefore inverse tangent of x plus 2 plus a constant.